Okay, welcome back to CE366, Lecture 4, Seepage. In this lecture, the learning objective is first, by the end, students should be able to construct a Phonet. So we need to define and then we need to learn what is a Phonet. And also through a Phonet, student will be able to calculate the amount of flow going through the geotech structure. And also within the geotech structure that we talk about, students should be able to find all the heads and water pressure within your project site. So first, in last lecture, we talked about 1D flow. So pretty much we spent a fair amount of time to talk about the Darcy law, which is Q equal KIA. So Darcy law works with one major assumptions. So for Darcy law, one major assumptions is we talk about one-dimensional flow. So what does it mean by one-dimensional flows? Means like we have Darcy law highly relies on the fact that the water is going strictly. So you only work for strict line flow. Which means, for example, if you have your project site right here, if you have a high water table, which means like a high amount of energy going to a relatively like a low amount of energy. So for given a project site, if the groundwater table is happen like naturally, for example, it's like certain miles array, could be 10 miles, could be like even 100 miles array. You have upslope, you have mountains, or you have a reservoir. Then the water will at a mega scale, we were going through a straight line because we are talking about like a really huge area, talking about miles after miles. So Darcy law works because water is flowing through a straight line. But for the case that like we have a geotech structure, for example, now we have a sheet power here, or you have like a dam or levees. Like now we talk about like a project site um, that we will alert the water flow. So for example, you have a sheet power wall there, so you have your upstream, and you are try to protect the properties or um, um, the village downstream. So within like a defined within a finite area for a project site. Now, because of the man-made structure, geotech structure, the water flow now within the project site is no longer a strict line. So the lecture 3, the previous examples within your project site, because like we were talking about very large scale, and the the flow of the water pretty much is a strict line. But now you didn't apply to the case that you have a man-made structure there now anymore. So we call this, instead of 1D flow, this is a seepage. This is a seepage. So for the scenario that like we don't have a strict line flow, so this is not a strict line anymore. Then in that case, Darcy law, oops. So in this case, so what has been working in the past? So we rely on Darcy law to do a lot of calculations. Since the water is not going through a strict line, which means Darcy law is not valid anymore. And like the previous lecture, we need to find out um, certain like a geotech interest, like the flow weight, Q equal KIA for Darcy law, but now it's not working. So we want to find out the flow weight. And also remember in the previous lecture, we spend a fair amount of time to find all the heads, the total heads, the elevation heads, and also the potential heads. We still want to find out those parameters, but now Dacian doesn't work, so we need something else. So in order to find those, what we need is a Phonet. So we talk about what is Phonet. But like at least like at this point, we need to understand that why we need a Phonet is because this is for Seepage. This is for Seepage, where um, the waterfall is no longer a straight line. Within the project site. So next we will talk about what is a Phonet. Okay, before we dig into the details of engineering side of using Phonets, let's step back, look at some of theoretical background. So in order to construct a Phonets, the theoretical base is actually thinking about the mass balance of water going through soil elements. So, because eventually we want to solve for all this like Q, which is the flow rate, and also all the heads on our soil site. So when I say soil site, you can think of like a picture like this. You have your geotech structure, and then you have your soil profile, like a certain type of like areas like kind of like interacting with your soil structure. Certain amount of soil mass that you need to take care of when the soil flows through your interested locations. So if we take a soil elements, for example, any soil elements, so we know like the water try to go from the upstream to downstream, so you pass through the soil. So if we take a piece of soil elements here, and then like go to here, so this is the soil elements that we're talking about. So on this piece of soil elements, let's look at like how the water actually is going through this little like a square. So pretty much like we try to like generalize the amount of water flow with one equations, or like we start to think about the equilibrium of water going through the soil elements. So the soil elements, first of all, this becomes a 2D problems. This become a 2D problems, two-dimensional problems. Unlike the lecture 3, right? We are doing with one dimension for 1D problems because we assume the flow of the water is a straight line, so it become a one dimension in a straight line. But Seepage now, right? We said like this is no longer a straight line, so you have a curve. So to define a curve, you need two dimensions. You cannot work just for one dimensions. Real world, is three-dimensional problems. Because it's like you have X, Y, Z. We live in a 3D world, three coordinate systems. But like for engineering analysis, if you make our life easier, if we just look at 2D, and many times we can make some simplifications that we simplifying our 3D problems into 2D problems. So now this is our 2D problems, and again we look at the soil elements. So the square that we're looking at now, and we have two axes. So let's say this is the x-axis, and this is the z-axis. So for this a piece of soil elements here, we have on this side we have say this as a length of dx, and the vertical length we say this element is dz. So we have dx and dz. And for the water that going in the z directions, so now becomes the velocity times the area. So suppose it's supposed to be a 3D problem, but we're simplifying the 2D. So the area that going through in the vertical direction now is the verticals like velocity in the z directions times the area, which is dx, right? And also there's a y-axis going into and out of the page. And since this is a 2D problems, so this is have a unit length of 1. So this just like the inflow. So again, the flow of the water flow going through the salt elements is the velocity times the area. So it becomes like a velocity in the z directions times dx. Similarly here, so we have the velocity of water. That will be in this like x direction. So we have vx, and then you will be times the area of dz times dy. And again, dy is equals to 1. So simplify this. So we have vx times dz. So this is the inflow. So this is inflow. So now this is the inflow in the x directions. And also we have the inflow of the z directions. And the outflow of it, so let me try to use the other color. So for the outflow in the x directions, so we have the inflow plus the change when you go through the salt elements. So this part here is the change of the velocity when you go through the salt elements. And then times the area again. The area is the dz times dy. And we have the same thing. dy is equals to 1. And for the outflow at the z directions, now we have the vz, the velocity of at the z directions, times the change that you take place when you travel through the these elements. So it will be the change of velocity, dvc divided by dz, and then times the dimensions of dz. And then this change of the this like alpha velocity within this parenthesis here times the area will be dx times dy, and dy is equals to 1 again. So from these solid elements, we establish kind of like the mass balance, inflow and outflow. And under equilibrium, under equilibrium conditions, the total weight of inflow will be equals to the total weight of outflow. So inflow equals to outflow. So if we do our math, we list out the equations here. Oops. So this the equations, which will be here, this part, and then you have another part. So the outflow in the x directions, and also the outflow in the z direction now. Will be equals to, so this is the out, actually this is the outflow. So this part is the outflow, will be equals to the inflow So Vx dz. So we're talking about this part now, and then plus the z directions of the info. So we talk about this part now. And in fact, if we do the math, you realize that in fact this terms here will cancel out, and this terms there will be cancelled out. So end up we will have these equations. And this part will be further cancel out. So at the end of the day, we have this famous equations. So let me write this a little bit better. Delta Vx over delta x plus the delta Vz over delta z equal to 0. And this is the famous Laplace 2D equations. So if we can solve for these equations, that means we solve for the solutions for the water going through our sites here. Because like at the end of the day, is the mass balance, is the equilibrium going through the solid elements within the site. And if we solve for this Laplace equations, then which means that will be we can find the solutions of what we want to find out. So we will elaborate more how to get from the Laplace equations to the flow rate and also the head that we want to get to. Okay, with the Laplace equations, then like the Laplace equations can be rewritten into a format for solving for the heads. Because remember, like all the heads, what one we want to solve for the Phonet or the 2D Seepage problems. So all the heads, like the Laplace equations, now we can read them in this form. And the H here is the total head. At any point. X and Z. So for example, this site here, you have again you have a sheet pile here, and then like you have a upstream water table and a downstream water table, and you want to know like how the water flow go around this like a geostructure. And you would do is you would set up a coordinate systems. So you could pick the origins. Maybe you can pick this one as the origins. Let me write this better. Perhaps like you can pick this one as the origins. Then you have your z and you have x coordinates. So the beauty of this is through the Laplace equations here. If you solve for this Laplace equations, then which means like you can solve for all the heads at any points within this like soil site where the geostructure at. And to solve this like a Laplace equations, so now the solutions is in terms of the total head. And if you see all this like contour line over here, those are the solutions of this Laplace equations. So since this is a 2D problem, two-dimensional problems, so your solutions is in terms of the x and z, and all this line right there representing the head, that would be your solutions of those equations. So if you're unclear on this point, please come to my office hour. But this is the concept behind what we're trying to achieve for this lecture. Again, for this lecture is we have a waterfall problem. There's no longer strict line. So if there's not a strict line, which means like a Darcy law doesn't work, because Darcy law only work in one dimensions, which is like a strict line flow. Now we've got a 2D problems. The water is flowing in, forming a curve. Then what you would do is like form a mass balance, equilibrium conditions. You solve for the water flow, inflow equal to outflow. Then you solve for the equations. You got a Laplace equations, and through the Laplace equations, you can find out the head at any points, because now the solutions is a Phonet. So the use of Phonet, we try to achieve two goals. First, so like using Phonet now, with the Laplace equations, then you can construct this Phonet. We talk about how to construct this Phonet, which means by the time you draw out the Phonet, this means you solve for the Laplace equations, and after that, you can achieve two goals. First is enables you to find all the heads. So the solutions give you the total head. And the previous lecture, we talk about how to find out the elevation head and also the potential heads, how it relate to the potential to the total head. So once you're able to find the total heads, you know the elevations, and then you can also find the potential heads at any points. The second goal is to compute the amount of flow. We talk about this, how to do that. So compute the amount of flow across the earth structure. Or the site, or the soil site. So this is the we'll talk about how much water is seepage through this earth structure. This is like a Q, capital Q right there. So what we're trying to do here now is we need to solve for Laplace equations, which is second order differential equations. And before the computational age, people used to do this more than decades, a couple decades ago, where the engineers doesn't have a computer, and they will try to solve this through a paper. Not only in the office, people need to find a quick answer right on the spot, right at the field. So to solve these differential equations, they come out with simplified graphical procedure to draw the Phonet. So once you're able to draw the Phonet, then pretty much which means you solve for these equations right there. So in the next two slides, we will talk about how to draw the Phonet. Drawing the Phonet is important because after you draw the Phonet, pretty much you solve for the Laplace equations, which means you can achieve the two goals right there. First, finding the heads, the total heads, and also the corresponding potential heads, because you will know the elevation heads. And the goal number two is to compute the amount of flow of water going through the earth structure or the site. Okay, before I talk about how to draw those Phonets, let's talk about the basic assumptions. So there's assumptions associated with what try to do. Otherwise, this graphical solutions of Phonet, it won't work. Or using, or actually, it's drawing a simplified Phonet. So what kind of assumptions we have for that? First, we assume the material zone, which means the soil, the properties of the soils is homogeneous. If this is not, then you need to take the average of the whole site and then make it as if one materials only. So this is a very there's a lot of simplifications or assumptions going on, but that's the requirements to use the Phonet. Second is we assume isotropic hydraulic conductivities, because we know that the water flow in the horizontals versus vertical directions, the water flow, the hydraulic conductivities of that are supposed to be different, because the mineral level of soils or the element level of soils, they are structured as like a horizontal layer, because soil is formed by lateral sedimentations, which means like the depositions. It's kind of like a layers after layers. So the water going through the layers, seepage through the horizontal directions, through the layers, will be very different than going vertically. So that's why, in the previous lecture, we talked about the equivalence hydraulic conductivities. You will have two different formulations when you find the equivalence hydraulic conductivities for the case that is parallel to the bedding versus the water flow is close to the bedding. So in the real world, the true soil behavior, the horizontals and vertical directions of hydraulic conductivity characteristics, they are different. But in order for this simplifications or this simplified graphical solutions to work, we assume they are the same. We assume also the whole site is fully saturated. So as long as you have water tables above the ground surface, this assumption is valid. And also we assume this is stylifold. And also we assume the fluid is incompressibles. And last but not least, we use the Phonet. And the Phonet will assume the Darcy law is valid. So you may say, hey, hold on. At the beginning, we say a 2D flow is a curve, and Darcy law doesn't work. So now this is the beauty of using a Phonet. Using a Phonet, what we do is the solution of Phonet, it create all these grids, all this finite elements right there. So within the assumption for the Phonet is within the finite elements, the water flow is a straight line. So within this part, this is a straight line. So within this part, we assume this is a straight line. So Darcy law still work within the elements of Phonet, because within so the assumption here is we make the grid small enough, well, meanwhile it's manageable. You can make with a computer our graphic complications. You can make the square as small as you want, but imagine you need to do this by hand. Actually, your homework and also your exams are required you to do it by hands, and within reasonable amount of time, and you need to draw this small enough that at least you can assume it's a straight line going through each of the elements. So this is the beauty of the using the Phonet. Now you break down your site into different smaller size elements, and that represent the solutions of the Laplace solutions. And meanwhile, the flow going through each elements, it fulfill the Darcy law, because now the water going through each elements, it is a straight line. So that's the beauty of any kind of finite elements and finite difference analysis. So that's much more advanced than this course, but at least like give you a sense on computations, what kind of computations work we need to deal with at the advanced level. Okay, so those are the assumptions for us to get started. And now the next job is to learn how to draw those phonets. So for the phonets, there's a couple more like a terminology we need to learn together. First, the phonet is bounded by some no-fault boundaries. So there is the no-fault boundaries. And within the no-fault boundaries, we have the what we call the streamlines. So like this one, let me clean this up a little bit. So like this diagram here. So these are the streamlines, which representing the waterfall. So those are the streamlines. And the streamlines, they are parallel with the no-fault boundaries. Meanwhile, they will be perpendicular to what we call the equipotential line. Which we used to reference by like the letter phi, and the streamlines we usually reference with this symbol. So those are the equipotential lines and also the streamlines. So when we draw the phonet, we need to make sure that the streamline, they are perpendicular to the equipotential line. And also the streamlines, they are parallel with the no-fault boundaries. And like between the equipotential lines and the streamlines, they will form a square. So I didn't do a very good job here, but like within the streamline and potential line, they kind of like define all the grids, all the square, and like to define as when you draw like those phonets to define those grid, which means like you can fit the circles within those like now there's like elements like that. So you would join all the grids is a square, which means it can fit a circle. Each of it should be able to fit a circle. And another major assumptions here we have is now we have the streamlines. So between the streamlines and also the no-fault boundaries. So all this we call it to be the fault tubes. We call this to be stream tubes or the fault tubes. Actually, sometimes streamline, some book will call it like a fault line. So streamline and fault lines, like they are the same things. And then like between them, you get the stream tubes or the fault tubes. So and each for each fault tubes, for the way it works, for now each like a fault tubes, it carries the same amount of fault. So which means here now, like here you carry a Q1, here you will carry a Q2, here you will carry a Q3, and then Q1 will be equals to Q2 equals to Q3. So those are some like basic principles when we construct the Phonet. And again, don't lose track the purpose of the Phonet. The Phonet is the solutions of the Laplace equations that you try to solve for, which representing all the heads, all the different heads within our geotech or geostructure that you have a 2D seepage problems. Okay, furthermore, again, one more times, you have all these equal potential lines here. Oops, supposed to be a straight line. For example, you have all these like equal potential lines here, and also you have those like streamlines going through. And like between each tubes, you have your amount of flow going through it. So this is your flow lines. And like further define this, two more like a terminology. First, n sub f is the number of flow tubes or flow channels or stream tubes or stream channels. There's many different like different ways that people call the same thing. So the n sub f is the number of flow tubes. For example, you have like two flow tubes right here, or if we have like the boundary right here, then you have four flow tubes for this picture. And another terminology is n sub d, which is number of jobs. So whenever like a flow line, or whenever like you pass through one of the equal potential line, you will experience an equal amount of job. So those are the purpose of the equal potential line, which tells you the amount of energy, which is the head at that point. So for example, here you have a total head of 100 meters. So after like dropping to another equal potential line, the head will be dropped to 90 meters. And then like, you go through one more like step, then go to 80. Then you know that the equal drops here is 10 meters. So the numbers depends on the site, but like the concept here now is the purpose of the equal potential line is telling you whenever you're passing an equal potential line, you experience the same amount of energy drop. And what is the total number of jobs for the site? How many equal potential line that you're causing? We call it n sub d, the number of job, the number of job. And more like forms are more like rules over there is first the no-flow lines, the no-flow boundary. In fact, is a streamline. It serves as a streamline. And also the total amount of flow, so the Q total will be equals to the number of flow times delta Q. So delta Q here is the flow of each tubes. Oops. Right here. So the in other words, is the n sub f is equals to the total flow divided by the delta Q. And one more observations is the head drops here. It is dissipated in equal increments. So we talk about this. So after we travel through each equipotential line, it will experience the same amount of drop. So which means the total head here, the total head drops here will be equals to the number of drops times the drops for each increments. So those concepts here will help us to do analysis calculations later. So you will need those equations for homework and also for exams. Another rule of thumb is when you construct those full lines of Phonet, it's always good to start with drawing the full line first, and you keep the numbers of full lines around 2 to 5. So those are some basic. So these two lines give you some a basic guidelines on how to construct a Phonet. Because when you're given a geotech problems, where likely you have all different kind of geostructure. So a professional grapher, or in the old days, each office we will have a professionals like a grapher just draw Phonets. And if you have a dam, and then people we come up with Phonets. And if you have a coffer dam here, people will come with another Phonet. And if you have very complicated dam that you have a core inside, this is the shape of Phonet. And if you have a simple sheet piling here, we have seen as examples at the beginning, this is another Phonet that representing this two-page the 2D Seepage, how the water flows through the structure for one structure and also the site. So if we do some quick exercise here, so we talk about the n sub f and also n sub d. So what is the total amount of flow going through the site? For examples, n sub f we want to find out. So n sub f is the number of flow tubes. So you have one flow tubes here. So if I use a color, if I can. So for examples, this is how the water flows. So this is one flow tubes, this is second flow tubes, and this is the third flow tubes. So n sub f equals to 3, and the number of drops. So how many equal potential line you go through. So again, those are the flow lines, right? So this is the no flow boundaries, and this is the no flow boundaries. This is the flow lines. And then this will be your equal potential line, those are your equal potential lines right there. And then the number of drops that you go through now, it will be 1 drops, 2 drop, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. There will be 12 drops right there, or you can double check yourself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Actually, I got 13. So let me try it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It should be 13. So there'll be 13 drops right there. So we can try this one examples. So this is the no flow boundaries right here. So this serves as the whole of the no flow boundaries, and this will be the another no flow boundaries right there.
Oh, actually, the no-fault boundary stop there. So this will be the no-fault boundaries right here. And then like the no-fault boundary is the fault lines. So fault line 1, 2, 3, 4. So you have like a four fault lines. And fault 2 will be 1, 2, 3, 4. So you have we have actually we have five fault lines. So 1, 2, 3, 4, and a no-fault boundary is another like a fault lines. And a fault tubes is always kind of like n minus 1. So you have n sub f equals to 4, and the number of drops will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So n sub d will be equals to 11. So I'll let you to try the other two examples. If you have any questions, like come talk to me. Come talk to me in my office. I'll let you give a try. So first of all, define the no-fault boundaries, and then find out the fault lines and also the equipotential lines. After that, then you can find out n sub f and n sub d. Okay, so we talk about those professional grapher. So in the old days, this is how people get the Phonet done. In the past, before the computation age, computer age, before the computational power take off, this is how the way it works for those professional drawings. So it can be done in an office, and also it also means to be done right on site when you need to do some quick calculations. For example, so like the rainfalls. There's an intensive rainfall, the water table rise, and then very likely we need to send some engineers go on the site to read the piezometers to learn about the water pressure by the water head elevations, and then from there they can compute drawing a full net on site or at the spot and quickly compute what is the amount of water flowing through the dam now is jeopardizing the people and the properties downstream, and also very important, they need to find out the heads at certain points of the dams. And if the heads at some critical locations of the dams has become too high, which means they can calculate the potential head because they know the total head, they know the elevation head, they can find out the potential head. And if they realize the potential head becomes so too high, so which means the potential head, we learned that in lecture 3, you can calculate the water pressure from the potential head. So after that point, if the water pressure is too high, which means like you can topple the whole geotech structure, which means the dam could fail. So very important, very important. Those are very important like uh, calculations for us engineers. Okay, so from the equipotential line, we can find out all the heads. And remember, for this lecture, for the purpose of using a full net, there's another goal we need to achieve. That is finding the total amount of flow going through the full net, which is going through our geotechnical structure or the site that we want to investigate. So now the mission here now is we want to find out the total amount of flow going through the flow net, and we start with again looking at individual like elements, individual of square within the flow net. So for a flow net, before we enter and exist the each elements, it has a total head. It has a head that going through the individual elements. So before enter and you live like you have some like head drops. So that's kind of like going through two equal potential line. Because if you understand this, if this is the grid, one of the grid, element grid of the full net, so this pretty much is these are your equal potential line, and this are your full nines. So you have like all those boundaries going through
your elements, finding your elements. But anyways, like if we look at this Phonet, then let's assume the dimensions here. Let's say this is the midpoint, and this has a dimensions of 2a, so half of it is a. And likewise, let's say this is the midpoint, so half of this are b, so the length here is 2b. And again, like we assume a is the mid width and the b is the mid height. And from Darcy law, the delta Q, so this is kind of like a full tube now. So the delta Q going through is equals to K times I. So the gradient is dH, dL, and also the area. So this is the Darcy law, Q equal KIA. And from this graph, from this like elements, so the dH is the delta H, is the head drop across the elements, and the length that traveling through these elements is 2a. And area, so the trick point now is the area. So the area that going through these elements is 2b times 1, because we assume this is a 2D problem. So you have a unit length that going into and out of the page with a length of 1. So this is the unit length into or out of the page. And remember, this is a square, so the dimensions are a is equals to b. So these two terms will cancel out. And now this become delta Q becomes K times delta H for this like 2D Seepage Phonet. So let's assume this is equation 1. And remember, like when we talk about those terminology, we have defined the total head before with these equations is equals to number of drops times the delta H. So if we organize these equations, then now delta H will be equals to the head drops of the total head drops of the whole site. So this like delta H here is the drops at one element. So at between two equal potential lines. But this like a total head drops here is belongs to the whole site. And then this is divided by H sub D. So now we have equations 2. So if we substitute equation 2 into equation 1, and we will get this equation. So delta Q will be equals to K times delta H total divided by number of drops. So we have equation 3. And now we make use of another equations that we talked about before. The total amount of flow equals the number of flow tubes times delta Q. So we got our equations of total of flow will be equals to N sub F, which is the number of flow tubes, times delta Q. So you got equation 4. So this is our equation 4 here. And then if we substitute equation 4 into equation 3, then we will get these equations. So the total amount of flow, which is we try to solve for. Remember, this is our goal number 2. We want to find out the total amount of flow going through the site will be equals to
N sub F divided by N sub D times K times the total head drops. So this is what we try to find out. So if we know N sub F, we know N sub D, we know the total head drop across the site, and also if we know the hydraulic conductivities for the homogeneous soils, we assume for the whole soil site, then we can find out the total amount of flow going through the geostructure. So next we will try one examples. Okay, let's try an examples together. So what we have here is you have kind of like a dam for this site, and we also have the upstream water and also like a downstream water level over there. So we are lacking on some information about the elevations. So assume this is 15 meters, this is 8 meters, and this is 7 meters. And also let's assume that from this point to this point is 3 meters. So that should provide like the information that we need. And also let's also assume this is a homogeneous soils. So the soils is pretty much like bound by those like a no-flow boundaries right there. So within like this site, the hydraulic conductivities for the soil is kind of like a silt type material, and the -7 meter per second. So this is the hydraulic conductivities. And there's to be two tasks to be done for this examples. First, we need to compute the total amount of flow going from upstream to downstream, which means like how much water is going through underneath the dam. And task number two is we will calculate the water pressure at point A, point B, and point C by making use of the Phonet. So speaking of the Phonet, so I cheated a little bit here. So it's supposed to be we draw the Phonet by ourselves, but I try to draw it like before, like I put this lecture notes together. So but like when we draw the Phonet, the first thing to do is go ahead to put on the Phonet first. So the green line here is the Phonet. So the first thing we should draw this like a full lines number one, and then maybe draw, and then the next thing is the full lines number two. Remember, the good practice to draw those full lines is keep it about from 2 to 5 lines, and then like we have the no flow boundaries, which is this is the no flow boundary number one, and also this is actually this is our no flow boundary number two. So those are also the flow lines, if you remember correctly. Like the no flow boundaries is also are also like flow lines. So we have those two, and then next is going to draw the equal potential line. So this is equal potential line number one, number two, number three, number four, number five, and number six. I didn't do like a perfect job. If we do like perfectly, each of the grid should like you should like perfectly fit a circle inside. So you see like some grids like you work well, and some grids we just have a hard time to fitting a circle. So it's not a perfect job, but this is the best I can do, at least within a reasonable amount of time. So if you draw something like that, I would think it's really good already. Given that like your homework and also especially the exams, when you have time constraint, just draw something reasonable. Draw something reasonable. Okay, task number one is computing the total amount of flow. So remember, like previously, we defined or we we devised this formula. So the total amount of flow will be equals to N sub F, number of flow tubes divided by N sub D, number of drop, times the hydraulic conductivities, and also times the total head. So first, a number of flow tubes. So we will have flow tube number 1, flow tube number 2, and flow tube number 3. So ends of F will be equals to 3, and number of drops. So we have 1, 2, 3, 4, 5, 6, 7. So the number of drops is 7. Oops, just 7. And the hydraulic conductivities is 10 to negative 7 meter per second. Then times the total height I mean like the total head jobs across the site. So the total head jobs is defined by the difference between the upstream water tables and also the downstream water table. And the difference between them are 7 meters. 7 meters. So after we do our math, our total amount of flow will be equals to, so this guy cancel out, so it will be equals to 3 times negative 7 meter per second. So that is a total amount of flow. So that would be our answer for task number 1. And remember, this is a 2D problem, so we define the dimensions into and out of the page as a unit unit dimensions Okay, so task number 2 will be finding the water pressure at point A, point B, and point C. So what should we do first for a problem like that? First, we define our datums. So here, for this problems, we define the bottoms, the datums at the bottoms, and to do problem like that will be like the problem that we have done in lecture number 3. First step, we will think like we need to like follow the water, follow like the flow of the water. So we start from very upstream. So right here. So and then also we care about the total head, which is equals to elevation head plus the potential head. So at the upstream, right? We define at the upstream is a water table is open to the atmospheric pressure. So the potential head over there is equal to 0, and the elevation head will be 23 meters for this case. So the total head at upstream will be equals to 23 meters. And then next, right before we get to the into the soils, so from here to here, so here is just water. So like the examples that we have done in lecture number 3 in our previous lecture. So from water to water, before getting into the soils, we assume there's no loss. There's no loss because you are not like getting into the soil, so there's no like total head loss. So the total head is still 23 meters. But what happened is within the 23 like total head of energy is the elevation heads and also the potential head. They are kind of like a changing or passing, changing like the positions. So some of the elevation energy now becomes potential energy because like you're getting to a lower positions. You're losing some elevation energy, but meanwhile, it's like you're gaining the pressure from the water because you're not at the atmospheric pressure anymore. So you're feeling the water pressure. So at this point, this is kind of like how many meters down. So here, from this point to here point, this point we know this is 3 meters. So this point is 5 meters right there. So the elevation head becomes 18 meters, and the potential head is 5 meters. It's 5 meters. So so we finish like the upstream, and then next we go to our downstream. So at this elevations right here, again the total head is equals to the elevation head plus the potential head. So at this point, we know that the elevation head is 50 meters. And we can continue our work right here. So we just look at the positions that we are exiting the soils, and now we are at the water level. We look at the water level, the water table is downstream. So very similar. This time the elevation head over there is 16 meters. And we know that now we are at the water table, so we don't have any potential head because it's open to the atmospheric pressure. So the total head got to be 16 meters. And between those 2 points again is just water, so there's no total energy loss, no total head loss. So the total head stay the same. And but what you change is the elevation has passing to the potential head. So they are changing within the elevations and potentials. So this is what we get. So we know like at this point is 16 meters. And here is like a 23 meters. So which means like the total head difference right there is 7 meters. Is 7 meters. Is 7 meters. Same as the total head. The total head that like we calculate before. So that should be 7 meters, which means like from the point that we enter the soil from upstream, from existing the soil downstream, we lost 7 meters in total. And we have, so the total head will be equal to 7 meters. And the ends of D, the number of drop is 7. Divided by ends of D, which means it's 1. Well, we don't have a unit for that. So which is 1 meters, which means like each head drops, we lost 1 meter for the examples. So this helps us to solve for the problem that we need to look at, because we know at this point when we are entering the soil, we have a total head at 23, and going through each equipotential line, we lost 1 meters. We lost 1 meter of head. So which means now like at the upstream we have 23 meters. Going through one equipotential line, then we have 22. So this is the total head. And then we have 21 meters, 20, 19, 18, 17, and then we back to 16. So this is the how powerful this like a Phonet can be. It helps you to illustrate throughout the flow of the water, going through the equipotential lines, how the total head change. So again, like from this examples, I pretty much I kind of like I make our life a little bit easy. So I make it up in a way that each like a drops go down by 1 meter. But this is just this examples, not necessary for any cases. So like in other cases, other cases depends on how you draw the phonets, and also depends on the head, the total head given to you from the beginning. And also like everything depends on water tables. If there's like a intense
intensive rainfall, so the water level at upstream have a, goes up, then everything change, and then you need to update your analysis again. So that's why many times, like as a geotech, you need to do this quickly in the field, because once the condition change, like you need to do the math to find out what happened to your structure, and also maybe what happens to the peoples and the properties downstream. So, but anyways, so this is what we want to get to, is find out the total head at each like equal potential line. So we are solving the problem that finding the water pressure at point A, point B, and point C. So let's look at point A. So at point A, we are looking at this point, and which is at the equal potential line of like a 19. So at point A, the total head at point A is 19 meters, and we know that the total head is equals to the elevation head plus the potential head. So we know the total head is 90 meters, and the elevation head at that point is 60 meters, right? Sorry, 15. It's 15 meters. So at that point, the elevation head is 15 meters. So we can solve for the potential head. At point A is 4 meters. And we know we're solving for water pressure. We know the water pressure at point A is equals to the unit weight of water times the potential head. So quick calculations, we can assume this is 10 kilonewtons per meter cube for the unit weight of water. To be more precise, it's 9.81. But sometimes if you need to do quick calculations on site, you can assume it's to be 10. And the potential head is 4 meters. So through the Phonet, so you see like just draw some quick picture, then maybe on your clipboard, then you can quickly to estimate your water pressure at point A is about 40 kilopascal. Okay, similarly, let's do the for point B. So the total head at point B is also 19 meters, because it's point A and point B. They are both on the same equal potential line, which is 19 meters, which is equals to the elevation head. So elevation head at point B plus the potential head at point B. And the elevation head is where the datum. So this is 0, and this is potential head at point B. So if we solve for this, so this equals 19 meters. So the potential head at point B will be equals to 19 meters. And the water pressure at point B, quickly, is about 190 kilopascal. So at point C, now we are at a total head of 17. So for the pressure at point C, total head at point C is equal to 7 meters, and that is equals to the elevation head at point C plus the potential head at point C. And the elevation head at point C is the same as point A. There would be 15 meters. So this would be equals 15 meters plus the potential head we try to solve for. So the potential head at point C is 2 meters. And similarly, the water pressure is equals to the unit weight of water times the potential head. So at point C will be about 20 kilopascal. So with that, we find out the water pressure at point A, point B, and also point C. These are quick examples.
Okay, lastly, I just want to show you like a little bit more advanced concept when in using Phonet. Remember at the very beginning when we talk about Phonet, we mentioned about we assume or we make simplifications that we have isotropic hydraulic conductivities, which means the hydraulic conductivities in the vertical directions and the horizontal directions, they are the same. In fact, they are not the same. And now using the full net, there's like some tricks. There's some like a procedure to help us to get around the shortcomings. So what we call this using some transformations like factors or scaling factors. So for the case that when we have anisotropic soils, means the K, whoops, means our KV is not equals to KH. The hydraulic conductivities in the vertical directions is not the same as horizontal directions. Now we need to consider them separately instead of like they are the same. So for the case that if we assume kx equal ky or kv equals kh, they're the same thing. Um, that case, these two are the same, they would cancel out, and it would become the Laplace equations that we have been keep working on. So now the case that like they are different, so we cannot cancel them. So so that's why you have those two terms over there, kx and ky. So, but we can do some mathematical tricks. So first, if we divide these equations by ky, so what we will have is become this formula. So still in Laplace equations like a format. Then what we do if we substitute x prime equals to the square root of ky over kx times x. If we substitute this, what we call this to be the transformations vector, then our equations right there, the star equations becomes, so now it's not x, it's become x prime. So it still become like a Laplace equations. So since the same equations, I mean like the same format as what we have been working on, so what it means is we can construct a full net based on the transformation factors that uh, we put on. So we still can construct a full net. So the procedure becomes first you will adopt a vertical scales. So you still when you draw, so now procedure like what I'm talking about is try to draw the picture um, of your of your geostructure. But like when you do your horizontals like a scale, then you need to do the transformations. So you will transform the horizontal scales by the factors that we were using, the square root of ky over the kx. So what does it mean is like for example, this is this is your this is the damp that you work on. So this is for the case that kx equals to I mean, the vertical and horizontals are the same, like what we have been working on. And if we want to consider the anisotropic factors, so now KH is not equals to KV. The horizontal directions is no longer same as the verticals. It's not homogeneous anymore. Then we keep while we keeping the scale on the y directions. On x directions, we transform it. So by a factor. So maybe like now this the scale has changed. So the vertical scales is still the same, but the horizontal scale is already been transformed by that. So excuse my drawing is not perfect, but the idea is like how the scale in the x directions has been changed. Then after you do the scale transformations, then you withdraw the sites with the scale we talk about on step number 1 and number 2. So which means like this procedure is exactly what I've done here. Just like draw the picture again, but the scale change in the x directions. Sometimes it's look like very awkward, but like that's the way it is for the transformation factors. And then like you will construct a Phonet. So pretty much like now you have the new scales, then you new scale, then you will construct a Phonet right here. One more time, excuse my drawings. So this is your Phonet. And based on this Phonet, then now you can do your computations. But now everything you will be come with the scale factors. So you can still calculate the same amount, I mean the amount of fold, but now you need to take care of the scale factor. So I believe like if you want to have more in-depth study on the subjects, like there's a lot of more like a detailed knowledge, and the textbook tells you a little bit more. And like if you are going to pursue a career, particularly in soil hydraulics or like a seepage, or like if you pursue a career, for example, in specialize in the design of earth dams or some other like trenches, like stuff like that, like highly related to hydraulic activities topics in geotechnical engineering, then you need to go deep. You need to go deep in this like a relevance like analysis. So with this we conclude lecture number 4, Seepage. If you have any more questions, I highly recommend you to come to see me in my office hour. All right, that's it for lecture 4. Okay, bye bye.